Welcome you in the lecture series of random processes, detection and estimation. This is 44th lecture of this series. In the previous lecture we have discussed about linear minimum mean square error estimation and sequential linear minimum mean square error estimation. In this lecture we will discuss about Wiener Smoother, and the outline of this lecture are Bayesian Gauss-Markov Theorem and Wiener Smoother. And in the objective of this lecture, you will able to explain what is Wiener Smoothing. Now let us start with the introduction. In previous lectures, we have discussed the technique for estimating random and non-random parameters. In many applications, the goal was to estimate a signal waveform from a noisy version of the signal in an optimal manner. Here we assume that the received signal is corrupted by the additive noise, and we would like to extract the desired signal from the received signal based on the linear minimum mean square error criteria. The received signal xn is observed over some discrete interval of time, n belongs to from ni to nj, where ni is the initial discrete time and nj is the final discrete time. The problem is to find x cap n, a linear estimate of xt. When n is outside the interval, we talk about prediction. So if n is less than ni, then x cap is the backward prediction, and if n greater than nj, then x cap is known as the forward prediction. And when n is between ni to nj, then the problem is referred to as smoothing. The process of extracting the information carrying signal xn from the observed signal st, where xn is equal to sn plus omega n, is known as filtering. And in this lecture we will discuss Wiener Smoothing. Now, Bayesian Gauss-Markov Theorem. If the data are described by the Bayesian linear model as x is equal to h theta plus omega, where x is n:1 data vector and h is known n:p observation matrix, theta is p:1 random vector of parameters with mean e theta and covariance matrix c theta theta, and omega is n:1 noise vector with mean mu 0 and covariance matrix c omega. Here c omega is uncorrelated with theta, and ex is the h of e theta, and cxx is h c theta theta h transpose plus c omega, and c theta x cross correlation, it will be c theta theta autocorrelation and h transpose. So the LMMSC estimator is theta cat is equal to e theta plus c theta theta h transpose autocorrelation, and inverse of the matrix h c theta theta h transpose plus c omega into x minus h e theta as from the previous lecture, and it will be equal to e theta plus inverse of the matrix c theta theta inverse plus h transpose c omega inverse h into h transpose c omega inverse into x minus h e theta. We assume n samples of the time series data xn is the transpose of x1 x0 to xn minus 1. Our y distance is stationary, and further ex is equal to 0. Then n:n covariance matrix take the symmetric topologized form. So cx rxx is equal to cxx, where rxx ij, it will be rxx I minus j, and this is the autocorrelation function rxxj. So autocorrelation function will be the autocovariance function here, and rxxk autocorrelation function is the expected value of xn, and xn minus k means correlation between xn and xn minus k is the autocorrelation function of xn, and rxx is the autocorrelation function matrix here. Here xn is wide sense is stationary and the expectation Exn minus k is independent of the absolute time index. In signal processing, the estimated autocorrelation function is used. The estimated ACF Rxx cap is given by when mod k less than equal to n minus 1, it will be 1 by n summation n0 to n minus 1 minus mod k xn into xn plus mod k, and when mod k greater than equal to n, it will be 0. Both the data x and the parameter to be estimated theta cap are assumed to be 0 mean. Then the LMMSC estimator is theta cap is equal to c theta x cross correlation and autocorrelation c x minus and x. The application of the LMMSC estimation to the three signal processing problems such as smoothing, filtering and prediction gives rise to different kind of Wiener filters. First we will discuss the linear minimum mean square error estimator. In this module we will introduce the Bayesian estimator derived with the linearity constraint, which depends on only the first two moments of the period. This approach is analogous to the blue in classical estimation case. These estimators are also termed as Wiener filter and find expensive use in practice. Now first we start the LMMSC estimation. Assume that the parameter theta to be estimated based on the data set x and the transpose of x0 x1 to xn minus 1. The estimated parameter theta will be theta cap is equal to summation n0 to n minus 1 an xn plus an, and it will be equal to A transpose x plus an. An is the weight coefficient, and where A is the transpose of A1 A2 to an minus 1, and we have seen this in the previous lecture. And so the estimation problem now is to choose the weight coefficient AY to minimize the Bayesian MSC. So BMSC theta cap, it will be the expected value of whole square of theta minus theta cap. So it will be E theta minus A transpose x minus an whole square, and the resultant estimator is termed as linear minimum mean square estimator. This is LMMSC. The MMSC estimator is linear when theta and x are jointly Gaussian. Now Wiener smoothing. The problem is to estimate the signal theta is equal to S transpose of S0 S1 to Sn minus 1 based on the noisy data. X is the transpose of X0 X1 to Xn minus 1, where X is S plus omega, and omega is the transpose of omega naught omega 1 to omega n minus 1 is the noise process. An important difference between the smoothing and the filtering is that the signal estimate x cap n it can be the use of entire data set, the past value, the present value, the future value. This means that the solution cannot be cast as a filtering problem, since we cannot apply a causal filter to the data, because it is depend on the past, present and future, all the values, and we are considering all the data set here. We assume that the signal and noise process are uncorrelated, so the autocorrelation function of x Rxxk, it will be Rssk plus R omega k, and Cxx autocovariance, it will be autocorrelation Rxx, and it is equal to Rss plus R omega. It's a matrix of autocorrelation function. And cross covariance, it will be C theta x, it will be the expected value of S x transpose, and it is E, and the expected value of S and transpose of S plus omega, and it is Rss. So the LMMSC estimator S cap, it will be Rss plus R inverse of Rss plus R omega into x, and this is omega x. and we have considered this omega is n is to n matrix. So omega is RSS inverse of RSS plus R omega. Omega is known as the smoothing matrix. Now, non-causal Wiener filtering. Consider a smoothing problem in which signal xn is required to be estimated given a noisy signal xn of infinite length, because we have considered all values here. So it is infinite from x minus infinity to x minus 2, x minus 1, x0, x1, x2 to x infinity as or xk for all k, you can say. And in such cases, the smoothing estimator takes the form x cap n is equal to summation n summation k minus infinity to infinity a k x k. Now, by letting hk is equal to alpha n minus k, the estimator can be expressed as the convolution sum. So as s cap n, it will be equal to summation k minus infinity to infinity hk x n minus k, where hk could be identified as the impulse response of an infinite length of two-sided time invariant filter. Now, using the orthogonality principle for the LMMSC case, that is the error in the estimator is always orthogonal, as you have seen in the previous lectures. So with the orthogonality principle, the expected value of theta minus theta cap xn, it will be 0 for all n, or we can have expected value Sn minus S cap n into Xn minus L, it will be 0 for all n. The equation required to be solved for determining the infinite Wiener filter impulse response, also referred to as Wiener-Hoff equation, and the equation required to be solved for determining the infinite Wiener filter impulse response, also referred to as Wiener-Hoff equation. It is given as summation n summation k minus infinity to infinity hk rxx l minus k is equal to rss l for all l, and take the Fourier transform of this, we will get the hf into pxxf is equal to pssf. Here hf is the frequency response of the infinite Wiener smoother, pxx is the power spectral density of the noise plus signal, and power pssf is the power spectral density of the clean signal. So as the signal and noise are assumed to be uncorrelated, the frequency response of Wiener smoother can be expressed as hf is equal to pss by pxsf, and pxsf include the pssf plus p omega omega f. So hf will be pssf divided by pssf plus p omega omega f. Since the power spectral densities are real and even function of the frequency, the impulse response also turns to be real and even. If this means that the designed filter is non-causal, which is consistent with the fact that the signal is estimated using both future as well as the present and past data. Now consider one example. Consider a noisy signal xn consisting of an desired clean signal Sn corrupted with an additive noise omega n. Given that the autocorrelation function ACF, it is RSSK, it is 10 by 27 into 1 by 2 is to the power mod k, and R omega omega k, it is 2 by 3 delta k, and assume that the signal and noise are uncorrelated and zero mean. Find the non-causal optimal Wiener filter for estimating the clean signal from its noisy version. So on computing the Z transform of ACF autocorrelation function, the power spectral density of signal and noise, it will be taking the Z transform of RSSK. So the RSSK, it is 10 by 27 into 1 by 2 is to the power mod k. So the Z transform, it will be SSZ, it will be 5 by 18 divided by 1 minus 1 by 2 Z and into 1 minus 1 by 2 Z inverse, and R omega k is 2 by 3 delta k's, and the Z transform of this, it will be P omega Z, and it will be 2 by 3. So the Z transform of the non-causal optimal Wiener filter is HOPT. It will be HOPT Z it is equal to PSSZ upon PSSZ plus P omega Z. So after putting the value in this, we will get 5 by 18 divided by 1 minus 1 by 2 Z into 1 minus 1 by 2 Z inverse, and divided by 5 by 18 by 1 minus 1 by 2 Z into 1 minus 1 by 2 Z inverse plus 2 by 3. So from here we will get this expression as 5 by 18 divided by 1 minus 1 by 3 Z minus 1 into 1 minus 1 by 3 Z, and the impulse response after taking the Z inverse. So we will get HOPTN, the impulse response of the optimal stable filter. It will be 5 by 18 into 1 by 3 is to the power mod n for all values of n. So far in this lecture we have discussed Wiener smoothing. This was 44th lecture of the lecture series of random processes, detection and estimation. In the next lecture we will discuss about Wiener filter and Wiener predictor. Till then, thanks for listening this lecture. Thank you.